Hi, everyone. Welcome to my presentation today. My name is Zheng Gao, and I work in Alexa AI as an applied scientist. It's my pleasure to present my work at ASRU this year. And the title for the paper is X-Short, Learning to Rank Voice Applications While Cross-Locale Shard-Based Code Training. So basically, as we are in Alexa AI, we are dealing with the natural language understanding related tasks. And in Alexa, the overall pipeline is to assign relevant skills. Skills here means the voice applications to the customer utterances as a to response. And it caused some challenges so far. The first challenge is that customer utterances handled in a popular locale may be going unclaimed in another locale, because Alexa, they split the whole market into several different locales, such as the United States and India. And even under each country, they are still have different locales belonging to different languages, like in US, meaning the English language in United States. And the locales are different, and some of the popular locales may have more developed skills, while some smaller locales may only have few developed skills. The next challenge is that locale with smaller skill ecosystem also suffer from limited label data for training system to route utterances to skills. For example, customers only provide feedbacks for the suggested skill without seeing the rest of skills. And therefore, it comes to our goal for this project. We aim to recommend relevant skills in a source locale for unclaimed utterances in a target locale, because there are more developed skills in source locale, and some of them may be suitable for the unclaimed utterances in some smaller locales. And we formulated our model as a two-step list-wise approach to first apply shortlisting to retrieve the top K most relevant skills for each utterance, and then leverage a re-ranking step to re-rank the filtered skills. So therefore, in the second re-ranking stage, we only need to minimize the prediction discrepancy for each utterance and its filtered shortlisting skill sequence. Loss function will be showed as below. Is a listwise as a sequential cross-entropy loss. And the framework overall is written in the pseudocode here. And the shortlisting, particularly, we directly use existing Elasticsearch to perform a keyword-based matching. And the re-ranking is that we develop a DNN model, and for each locale, we train a separated re-ranking model with the same architecture, and it's trained in an incremental training way. And the pseudocode for this algorithm showed here to the right. The input is across local utterances here. We have utterances from the source locale and the target locale with their ground truth labels. And we also construct the source locale and target locale Elasticsearch index. And we also have need to initialize two re-ranker models for each locale. The first step, as we aim to do a shard-based code training method, meaning that first one, we do a data splitting to split the whole data into n equal data shards. And for each data shard, we have applied the shortlisting to each utterance first. And each utterance, we will retrieve them the top K skills from both in the source locale Elasticsearch and target locale Elasticsearch. So in the end, each utterance will have two shortlisting skill lists. And then in the re-ranking step, we apply the upsampling and the pseudo labeling to augment for data augmentation. And then we train the re-ranker model, use the augmented data. And for the last step is the initial incremental training. And we use the previous shard train the model as the initialization of the next shard DNN re-ranker model training. So the shortlisting in detail is a Elasticsearch using TF-IDF model, and it based on the rules. A rule is rule-based matching between the artist text and the skill definition and their categories. And the re-ranking step is we apply the data augmentation. So first one, we use a biased upsampling. So we upsample training instances with positive labels, because for each artist, sometimes the user can provide the positive feedbacks, but sometimes they provide negative feedbacks. And we only upsample those positive label artists. And the pseudo labeling is in our re-ranker model. We use a co-training in a shard-based manner. And particularly for the re-ranker model, we use a transformer-based encoder, and we develop the fusion layer to capture the artist and the skill interactive features. Also, we have a sequential decoder to consider the shortlisting sequential results to trying to predict the sequential labels for the shortlisting skills. And in the end, we use a cross-entropy loss, sequential cross-entropy loss for the final loss. And the training strategy is that we use, as I said, we use incremental training among data shards, and we use pre-trained BERT embeddings. And we have applied the early stopper to avoid overfitting. So here is the detail, the pipeline of how a ranker model is trained in one data shard. We particularly focus on, so it's a symmetric. So the things trained in the target locale is the same thing trained in the source locale. And we use a target locale as an example here. So first, we have target locale artons, and then each artons will pass to two different Elasticsearch and get two different shortlisting skills. And you can see that some of them, like blue here, is a label skill, meaning that user already provided positive feedbacks here. But if it's a blank, it is white color, meaning that user do not have any feedbacks or negative feedbacks here. And then we use this one. We use the target locale skill sequence to do a biased upsampling. For each skill shortlisting sequence, we pass to the individual pre-trained rankers in the previous shard, and then we predict some pseudo positive labels here and add it to the current skill sequence as the pseudo labels, and that's for the further training. So in the end, we merge the pseudo labels plus the biased upsampling results together to achieve the augmented data here. And this data will be used for incremental training, and it will pass to the re-ranker model. The re-ranker model here is a list-wise model. So the input is the artons and also the shortlisting skill sequence. We have V1 to Vk, and those are the skills in the target locale. And then each skill we will pass to a transformer-based encoder, and then we concatenate their different features and pass to a fusion layer. The fusion layer is that we calculate their different interactive features between the artons and the skill, and then we have their interactive representation as the output of each fusion layer, and then we pass to a bi-LSTM for the final label sequence prediction. And YK here, meaning it's a binary label, whether it's a positive or negative, it's a 1 or 0. And in the end, we apply this approach on our experiment. So we construct two real-world cross-local data sets from Alexa. And the first one is using the United States as a source locale and Canada for the target locale. The second one is United States as source locale and Great Britain for the target locale. And this is the whole data statistics. And the settings is that we compare with several different baselines. So first one is Elasticsearch, meaning that we only consider the shortlisting step. The pointwise model is that instead of we remove the Elasticsearch result for the skill candidate filtering. We just randomly pick up one out among thousands of the skills as negative examples. So that's the pointwise model. And the pure learning is another way for the data augmentation, same as relabeling and upsampling, especially relabeling is use a face model and plus the cosine similarity to add some relabels here. And we evaluate our results using the precision, recall, and F-score for the classification metrics. And we also have some ranking metrics, and we also propose some human metrics. But those metrics are evaluated for all the models and baselines. So from the model comparison here, we can see that most of the time, our proposed model works better. So due to the confidential issue, we cannot directly report the absolute value. Instead, we report all the comparative performance compared to our proposed model. If it's a positive sign here, means that the baseline outperforms this much percent. Because if it's negative, meaning that it underperforms. So from this table here, you can see that basically all the metrics, our model outperforms all the baseline models. There are several exceptions, but for example, listwise model have a higher precision, but sacrifice recall a lot, resulting in F-score less. So we also run some side experiments to test the model, to dive deep into the model prediction statistics. So there are actually two types of skills. So first one is the common skills shared across the two locales, and another one is unique skills only appeared in a single locale. So here we represent that the common skills and the common labels to highlight that the ratio of the skills the positive predicted skills are the positive or the common skills, or the ratio of the predicted labels are from the common skills. So that's for the unique skills, and that's for the label count. The difference between the testing data and the inference data is that testing data is still the label data that users provide feedbacks, and the inference data is that user cannot provide any useful feedbacks. And that's how it looks like. The percentage of the retrieval here in the testing data is much higher than the inference data. This means that for the testing data, most of them will be suggested with the positive skills. But here for the inference data, only like 40% of them will be recommend some positive skills through our model. And we also run some evaluation study here. We remove some of the model inputs like skill ID, name, and the Elasticsearch score. And we also remove the fusion layer and the BioSTM layer here. And all of them mostly will result some degradation towards our default model. And we also run some parameter tuning to tune some upsampling factors like the ratio we upsample those positive utterances, and the shard number, that how many shards we split the whole data into, and some uncertainty threshold, meaning that only the predicted results with a prediction score above a threshold, we will treat it as a pseudo label. And the pseudo label combination is that how we treat the because we have two local predictions, and how we can merge these two local prediction labels together to add it as pseudo labels. And those are the parameter tuning here. We also try some dynamic label change, meaning that we want to track how many of the positive labels the model can predict for each data shard. So these are the data shards, meaning that when we train more data on more data shard, it tend to predict more positive labels towards the utterances. It feels like that our model, the re-ranker model, will be more powerful with more data shards trained. And that's all. Thanks.